Hello, I'm Renzo Huber from NIH, and this is an ISMRM presentation entitled Advanced Echo-planar Parallel Imaging with Gradient Harmonization, aka FRISGO, an optimization approach for fast, high-resolution fMRI, and I have no financial interest to disclose with respect to this presentation. High-resolution fMRI has the potential to capture the whole brain layer-dependent directional connectome across the entire cortex. However, previous attempts at whole brain layer-dependent fMRI were challenged by artifacts from too much subsampling or just having too long TRs. And it has been a very personal journey for me. In fact, I'm trying this since about 5 years now, half of my career. And this abstract now is the latest iteration of trying to get to the bottom of this, to understand what's holding us back and solving that. To understand what's holding us back, let's look at this example over here. This is a 200 slice protocol at 0.8 mm isotropic. It's fully sampled, and because it's fully sampled, it takes about 40 seconds to acquire a whole brain. And then we can take this to see how much to expect if we measure the G factors for a given set of undersamplings and then see how much noise amplification we would have, assuming the ultimate SNR that one can get. And you can see that kind of SNR increases. However, we shouldn't really be SNR limited up about maybe GRAPPA 2024 or so, where the G factor really starts to explode. So in theory, we should be able to be much faster, certainly better than 3 seconds. However, why is nobody doing GRAPPA 16 then? In the layer-dependent fMRI literature, I think the largest value that I see commonly used are not exceeding GRAPPA 4. And the reason for this is because this is just theory, right? And in practice, we are not limited by thermal noise, but we are limited by different things. Namely, when you just go to the scanner and run those experiments, you do see that beyond GRAPPA 4, you start to see these artifacts creeping in that really take over and make those data unusable. So we are not really limited by the number of channels or GRAPPA RF encoding power, rather we seem to be limited by these artifact amplifications. So let's look at this a bit in more detail. We do see that those are the usual suspects. For example, we see these fuzzy ripples that come from third order shims and gradient oscillations. We see those edge artifacts over here that come from uncorrected eddy currents. And we also have these higher order phase inconsistencies over here. So all of those issues are gradient issues. They're not GRAPPA issues. It seems that GRAPPA is just amplifying those gradient issues. Namely, GRAPPA is an idea that works by deliberately causing ghosting artifacts and then unaliasing those ghosts based on the different coil sensitivity patterns. This means, however, that when you have these tiny additional unknown ghosts in the base image, GRAPPA chokes and amplifies artifacts, resulting in those kind of fuzzy ripples over here. So better visible here, tiny ghosts in the base image result in huge ghosts and artifacts in the unaliased image later, especially for large GRAPPA values. All of those issues, however, are solvable, so we can look at them one by one and try to account for them. Namely, these fuzzy ripples are mostly caused by gradient oscillations and imperfections that are caused from inductive coupling of the third order shims that can be accounted for by unplugging the third order shims with conventional improvements of artifact quality as shown over here. Next, let's look at eddy currents. And as you know, when you want a nominal EPI gradient waveform like that, usually what you get is this kind of dotted line. And there is integrated correction methods from the vendors, usually a long-term eddy current compensation method and also a delay correction that tries to basically shift it to make it look better. However, we still have these short-term eddy currents, like half a millisecond, that are usually not corrected for by the vendor approaches. However, in collaboration with Siemens Healthineers, specifically Michael Köhler, we included additional short-term eddy current compensation into the vendor way of doing it, allowing us to get closer to this nominal trapezoidal shape like this, with typical improvements of edge ghosts, as you can see them over here. But there are even more issues. For example, these GPA overshoots or B0 terms that accumulate across the echo readout, resulting in a smooth phase evolution in the center, but then we have these different bumps, different for odd and even lines, and these sparse phase jumps resulting in ghosts. And as previously shown, such even odd issues can be accounted for with a dual polarity approach where we alternate read directions across TRs, where pairs of images can be seen as mathematically identical to just using only the odd or only the even lines. And in such an approach, we have a smooth phase evolution and consistent images. So if we do this in practice, you can see that we have these ripple artifacts, and they are exactly opposite for the different polarities, so you can calibrate them away. And these calibrations can have multiple forms. For example, you can take triplets of images, estimate the error field, and then removing it of individual images with opposing polarity, different signs. Or you can do this on a run-by-run basis, or you can just average pairs of TRs. And here I'm going to show you how this results in different time courses as implemented in FRISGO. For example, when you have a run-wise calibration, it accounts for most of it, and you just have these tiny residual odd even jumps up and down. When you take a complex valued average of pairs of images, you can see that we have a loss in temporal resolution. You don't want that, right? So rather you can take triplets of images, estimate the error field, and then only apply the error to odd and even TRs differently. Or maybe most convenient would be to just do this as part of your slice time correction, where you adjust your triggers exactly between the k-space centers, and then you're accounting for these odd even jumps inherently. But overall, either way, it's just fine. fMRI is really slow anyway. Combining all these three strategies now, unplugging third-order shims, using short-term eddy currents, and doing this dual polarity calibration then gives us a method that we call FRISGO, fuzzy ripple-free imaging with short-term gradient optimization. And we can see how effective this is by looking at the same dataset that I showed you at the beginning with the different Grappa values. Namely, you can see that it nicely cleans up most of these artifacts very efficiently. And you can see that we are not really limited by thermal noise all the way up to Grappa 16, and maybe at Grappa 20 the images are still fine. Maybe in the center we have a lot of G-factor noise amplification, and only at about Grappa 24 things fall apart. So you can certainly push whole brain layer dependent fMRI into the regime of TRs less than 3 seconds, as you can show here, which was not possible without FRISGO. We then wanted to validate FRISGO in 20 sessions using 6 participants with a checkerboard and a tapping experiment, and we used the sequence as we make them available on the Siemens App Store that is already FRISGO compatible, and we are doing the standard LN FRISGO implementation in Laney for this calibration. For whole brain layer dependent fMRI at 0.8mm resolution with less than 3 second TRs, you can see how it provides stable and robust results across all participants here. If you care less about high spatial resolution and want to be rather faster at larger voxels, you can see that also here with Grappa 16 you can get very stable results for these paradigms. If you want to push the spatial resolution much more, FRISGO allows you to go to 0.39mm isotropic resolution with very stable result across participants. And here you can see a lot of features that we could not see before FRISGO. Namely, FRISGO is not just an incremental improvement, we see new things. For example, we clearly see now that these largest voxels, which are responsible for maybe the 90% of the overall bold signal, are always overlapping with these large draining veins that we nicely see in the underlay of the EPI mean now. And even in the EPI itself, you can see the layer structure quite nicely. Now, the second largest class of voxels is then still not really looking at gray matter. It's rather looking at these large draining veins as they are diving into the gray matter, those diving veins. Only the third class of voxel, the weakest activated voxels, are then giving us these indications of these stripes within the cortex, indications of maybe a layer 4. Maybe also a surprising result of having data that we had never before at these high resolutions is how many negative voxels we have. We don't really see them at 0.8mm layer dependent fMRI, and in fact those very voxels are positive at 0.8mm resolution. Only at very high resolution they turn negative. And based on their temporal and spatial signature, we seem to think that there are a blood volume effect of large draining veins. As weird as it sounds, large veins seem to dilate. Having these validation experiments all in the same participants allows us also to compare this across different resolutions here, for example, to see how these bumps of the stria responses are then disappearing as you go to 0.8mm resolution, while still having some hope of partial voluming these large draining veins away that are so strong above the cortex. As you go to 2mm voxels, very fast imaging, you can see that layer results are not really sensible anymore. However, you have more feeling for the high temporal features. Namely, we see the surprising results of these oscillation patterns over here in the delta regime, which are too fast now to be explained by cardiac. And now that we know that FRISGO seems to work across participants very stably, we can also try to apply it in application studies. For example, in this study that's shown from Hassar Ahmadi at this conference, we are looking into vaso layer-dependent fMRI in the hippocampus during autobiographical memory tasks. Using 200 slices below 3-second TRs here, we are not only seeing the hippocampus, but we are also interested to see how this interacts with the cortical networks. In fact, with the short TRs that we are having, we can not only look at the different trials, but also different epochs within the trials, how these kind of attention networks are engaged during the periods of finding a memory as opposed to the response conditions with the button presses. At the Fine-Bergertron scanner, with the impulse gradient, you can actually push FRISGO even further and on the other side of the forbidden frequencies, which then allows us to really acquire vaso within one single inversion recovery whole brain with 200 slices at 0.8mm resolution, where we do see the canonical resting state networks without veins at layer resolutions. Applications of FRISGO at lower resolutions allow us even to go to GRAPPA 21, here with Stephanie, looking at CSF volume changes. And with conventional whole brain EPI, we cannot really capture the CSF-specific T1 relaxation that's different across the different compartments before everything is going back to equilibrium. Only with FRISGO, we can really capture these critical time points where CSF, blood, and gray matter are having a different T1 relaxation, and we are so fast that we can even do this with multiple echoes, allowing us to extract CSF volume differently from blood volume and bold, and we see, while people get sleepy, a quite dramatic change in CSF volume. FRISGO is also so effective that it does not only clean up functional EPI, but it also cleans up EPI so well that we can use it for structural imaging by removing these artifacts that I talked about, giving us MP2 range-like images with volume TRs in just 20 seconds, allowing us to also do functional analyses of structural features. For example, having whole brain free surfaces every 20 seconds then allows us to see how gray matter expands, specifically how the gray matter white matter border seems to move inwards during functional activation. The challenges of FRISGO include having a large amount of data. We have 16 times the number of voxels as HCP per second. So individual runs that are longer than 7 minutes actually are not really describable with Nifty anymore, because in Nifty you have this limit of having a maximum number of 2 to the power of 32 voxels. So for Laney, we actually had to update it to also support 2 to the power of 64 voxels. And for other software packages, we sometimes run into limitations if we have longer runs. Overall, however, the amount of data is not really that limiting in the age of having cheap hard drives. And also, OpenNeuro didn't really complain yet by having kind of these terabytes per participants. In conclusion, with the conventional 7T scanners that we all have, we are not limited by SNR, we are not limited by the number of RF channels, we are not limited by the gradient strength. What we are limited by is the gradient quality, which is solvable with FRISGO, just optimizing these short-term gradient imperfections. And FRISGO allows us to do whole brain layer-dependent fMRI at just 2.5 seconds. And we can also push resolutions to 0.39mm at conventional 7T scanners. And there's no deep learning, no low rank reconstruction, no subspace recon. It's just plain old EPI with the knowledge where the artifacts come from, with online reconstructions and DICOMs directly at the scanner, with well-behaving Gaussian noise independent across TRs. You can add all these fancy tricks later, additional to FRISGO. And with this, I thank you for your attention.